Good morning, friends. So today is the third day of our Web-Colloquium, and every day the number of participants are coming down. I don't know, or even is it because of some technical issues? Let us see, because it is raining in Kerala, I think, throughout. Yeah, it's still raining. So good morning, and again we have Professor Vijayan with us. He has given an excellent introduction to this colloquium on the first day, in the first session, and we are actually, he studied the entire topics and given a wonderful introduction for this colloquium. And he also helped us to get a very good speakers for the colloquium. And I take this opportunity to thank you, sir. Actually, otherwise, see, anyway, one by one, the participants will feel how we selected and with the help of whom we selected participants. Sorry, speakers. And again, those who have not turned up on the first day, anyway, I will read Professor Vijayan's biodata once again. So, Professor Vijayan is from Department of Physics, IIT Madras. His early education is in Kerala and obtained the first few ranks throughout the school and college education. Awardee of NCERT NTA scholarship during his college education, MSc and PhD from Department of Physics, IIT Madras. Then he served as a senior project officer at IIT Madras for 2 years and as lecturer in Pondicherry Central University for 5 years, and joined as assistant professor at IIT Madras in 1993. Currently senior professor. Field of research is photonics, light matter interaction. Guided successfully 14 research scholars for PhD, presently guiding 3 more. Published over 100 research papers in international journals and presented over 100 in conferences. Some of these have received Best Paper and Best Presentation awards. Over 100 invited talks in conferences, universities, educational institutions in India and abroad. Invited to give the inaugural lecture in NCERT Golden Jubilee Lecture Series in New Delhi in 2011. Involved in active research collaborations with universities abroad, has been visiting professor in Singapore and Germany. Another author of a book on nonlinear optics published by John Wiley International, now in 2nd edition. Currently the president of the Tamil Nadu Pondicherry Regional Council of Indian Association of Physics Teachers and honorary fellow of Kerala Academy of Teachers. So this is a short biography. He has written several books in Malayalam also, and even several articles in local languages. And as you know, as I mentioned in the first day, he usually takes lectures like this and motivates students and young researchers to further research interest in wonderful area. So with this, I invite Professor Vijayan for delivering his lecture. Please, sir.
Good morning and welcome to all of you to this lecture. I will start when I see some number of faces. Statutory warning, this talk will be a serious talk and it will not be like the first talk. So if you expect a talk like along the style of the first talk, that is not going to be the case. That was an introduction, and this is, as I said, general will talk about the major issues and then the major talks about the general issues. So this is a major issue, general talking about the major issue. So let us proceed. I will show my window. The topic is nonlinear optics or nonlinear light matter interaction. What I plan to do is to provide the basics to understand it for the first half. Just the basic, so that you can understand the phenomena properly. And then I will go to a few phenomena. Maybe 1 or 2 I will have time to explain in some detail. And then I will talk about some recent developments and all that later. So that's the plan. But at the end, I will give you a magic wand to understand all this properly and in a nice manner. So don't worry, even if you don't understand some of them. Basically, it's actually a tough subject to understand, especially the theory of it. The electromagnetics and quantum theory of nonlinear light matter interaction are not that easy. It's not trivial. So that is something we have to. But anyway, at the end, I will give you a magic wand to understand all that. So let us proceed step by step. Now, I would like the audience, someone in the audience, to tell me why am I showing this picture here. This is not on magic. Muthugada magic or something like that. This is on nonlinear optics. So why am I showing this picture? I want some student from the audience to unmute and answer this.
This is Donna Strickland, the Nobel Prize winner.
Oh, very good, very good.
2018.
Very good, nice. I see sparkles of Donna in the audience also. Very good. That's very nice to see. Yeah, so that's why I'm showing this. At the very beginning, I should tell you why this topic is included in this. It's a very topic which is very much alive today in recent years. You all know that Donna got the Nobel Prize, and so far only Madame Curie was there as a most famous person in known to physicists, but of course there are other people. But she became very famous, and these are the people who got the Nobel Prize. And we will be talking a little bit about that, because that is related to nonlinear. That is ultimate nonlinear optics. Of course, it didn't happen in 2018, but that is being used in even 2018 in a big way. It happened long back. So that is the importance of the subject. Now the basics. Do the students understand these pictures? Are there these things there anymore in the textbook? These are the simple diode and triode. Why am I showing this old stuff? Just to drive home some ideas. This is a simple diode. You have the transistor diode, which is an equivalent of this. The process is basically similar. What I want to convey through this picture is basically the similar. But I thought I can present it in an understandable manner if you look at this picture. This is the diode. There is a heater, a cathode, and an anode. See, this is what happens. So the electrons flow, and there is a flow of current. Electrons flow, and there is a flow of current. Now the question is of control. How do you control the flow of electrons? How do you control the flow of electrons? You can do it easily because electrons are afraid of electric and magnetic fields. So you can control it by putting a grid there in the circuit. And this is the transistor. This looks very similar with a minor difference. Like you give an answer, and if it is not the correct answer, you come and argue for marks. No, it is almost approximately that. This is actually not approximately that. There is a lot of difference. If this were not, this idea of control were not discovered, then you wouldn't have all those electronic equipment. It's so important. This will have limited applications. But the moment you introduce a control, then you can control using a small current, you can control a large current and things like that. And that you know you are more familiar with the semiconductor version of it, the transistor circuits. And all this is possible: amplification, oscillation, switching, modulation, communication, computing. All that is possible because you can control. So the key here is control a large current using a small current. Then you get this. Now, if you look back at your circuits, you will understand really what exactly I mean. But we are not talking about electronics. We want to know, is photonics possible as a technology? Can photonics do control? Can we do communication and computing? The answer seems to be no at the beginning, because photons are not afraid of anything. Yesterday, Professor Vijay would have told you that the photons are not afraid of anything. They are afraid of only one thing: the refractive index, change in refractive index. When the photon sees a change in refractive index, they start behaving in a funny way. So that's the photonic crystals. You keep alternate alternate refractive indexes, and then play with the photons. The photons are not afraid of anything. So you can't have this kind of thing. So it looks like it's not possible. Imagine the moonlight coming through the window, and then you shine a torchlight. Torchlight goes its own way, moonlight goes its own way. As you are traveling, you are passing through the corridor, and your enemy is coming in the opposite direction. You go as if nobody is there, and that person also goes as if nobody is there. This is called the principle of superposition. Independent, each one does its job independently, and there is no mixing or no transfer of energy. So this is the starting point. So if you want photonics, you have to somehow break this and make these waves talk, make these waves interact and exchange energy. Or The question is, can light control light? Can a beam of light control another beam of light? Can photons control photons? Then only you can have photonics, as we have learned the lesson from electronics. So that's the question. And the answer is, yes, it is possible. It is possible. You can have a transistor. You can have a things like amplifier. What I have shown, there is an amplifier, that kind of thing. And for that, you need nonlinearity. That is the significance, or that is the motivation of doing nonlinear optics. Control and photonics. All how to control a photon. How to go to the realm where the superposition is no longer obeyed in that way. So welcome to the nonlinear world. Now I step back from nonlinear optics. That is the nonlinear world. Where is that world available? The whole world around you are nonlinear. We are nonlinear. Why do I say we are nonlinear? Plot a graph between your age and your height on the y-axis and your age on the x-axis. So what will happen? If it were linear, whatever your height at age 1 and age 100, everyone will be very, what do you call, Muslim Batti Pengutti or something like that, that kind of very tall, Uyarnda Manidan in Tamil we say, Uyarnda Manidan. So, but that doesn't happen. Actually, if you go to 100, your height comes down. Even at 60, 65, you see, the height will come down. So that's the reality. That's why I'm saying we are nonlinear. So the point is, nonlinearity is not a special thing in optics. It is just, it's like calling biology, the biology of non-elephant animals. It is a common thing rather than the exception. So your growth, your height, homework for the students, the plot between your height and your age, does it pass through the origin? That you can work out and tell me later. So this is the issue. So the issue here is that you are not linear. They are all examples of non-linear objects, if you look at this aspect of it. So there will be some line. We will cross the line when we come to it. You might have heard about stimulus versus response. There is a stimulus and there is a response to it. And if you give an extreme stimulus, what happens? That's the question. In statistical mechanics, we call the linear response theory. We talk about transport properties. What are transport properties? Somebody is running away with something. Somebody is running away with mass. Somebody is running away with charge. Somebody is running away with gold. No, sorry, that is politics. That is not transport property. So somebody is running with momentum. Somebody is running with energy from one end to the other end of the sample. That is called transport property. Once, a thief came to P.T. Usha's house and stole some gold medal and started running. So P.T. Usha, he didn't know that it is P.T. Usha. So she also started running. And then what happened? This is a transport property. He taking away the particles. And then when she caught up with him, she thought she's in a race and she started running faster. And he went in some other way. This didn't really happen. I don't want to insult a celebrity or something like that. So transport property means you are someday running away with something. In other words, you're transporting through matter, transporting energy, particles, and all. So linear response, why do we learn only linear response even in the MSc? The simple thing, we only know one equation, y equal to mx plus c, very nicely. All the other equations are complicated. So we stay with y equal to mx plus c. Other things are difficult and complicated. Whereas the real life is not like that. Now let me come to a specific kind of plot. Strain is plotted as a function of stress. In the usual textbook example, we are hanging a wire and putting weights on the wire and all that. So the strain is proportional to this. That everybody knows, you all know that what happens when there is too much of strain. So let us look at the plot. This is the plot of, I have noted something else, but let us talk about stress and strain for a minute. So strain on the y-axis and stress on the x-axis. So you all know what happens, there is too much of stress. If there is too much of stress, the response deviates from linear, and you have a Hooke's law region where the stress is okay, and beyond Hooke's law. So what happens if there is too much stress in life? You go beyond Hooke's law and hang a hook and hang on it. That's what people do when there is too much of stress. too much of stimulus which you cannot have. So that is, of course, I'm talking about not the life stress, but I'm talking about mechanical stress here. Similarly, when light enters, light interacts with matter. What happens when light interacts with matter? Light is an electromagnetic wave. You have the electric field jumping up and down at 10 power 14, 10 power 15 per second. That's the frequency of light. And that is interacting with matter. And what does matter consist of? Matter consists of positive charges and negative charges. There may be dipoles already there, or dipoles can be induced. So what does this electric field do? It just pulls apart the positive and negative. Michael Jackson comes singing and dancing into the audience, and all the members of the audience also started jumping and up and down at the same frequency of Michael Jackson. So that's what happens here. The electric field is jumping up and down, and that is pulling the positive and negative apart. So that is what is happening in matter. Even when glass passes through a medium like that, it happens. I mean, when light passes through glass, it happens. And now let us look at this equation. This is polarization, the polarization, and this is plotted as a function of the electric field of light. Remember that. This is a function of time. It's the electric field of the electromagnetic wave, that is light. And you have a linear response. But what happens when you shine high intensity light? Then it deviates from the line, and then you have nonlinear optics. When it deviates from this line, you call it as nonlinear optics. And instead of Hooke's law regime, in optics we call it as a linear regime. How do you describe the linear regime? That's fine, this equation is fantastic. All your, this is related to refractive index, you know. So all your optical properties which you study up to BSc can be explained nicely with this equation. The polarization vector, the polarization, the dipole moment per unit volume, that is what it is. And this you know what is epsilon naught, the absolute permittivity of free space, and chi is a new thing which we are going to talk about. Chi is called susceptibility. Susceptibility, how susceptible it is, the medium is. So it is a property of that medium, and different media have different susceptibility values. And the susceptibility, why is it called susceptibility? It's a question of somebody sneezes 5 times, do you catch COVID? Or somebody sneezes 500 times, do you catch COVID? If you catch COVID at the first sneeze itself, you are susceptible to COVID. That's what it means. So similarly, the electric field, same electric field, how much polarization can it induce in matter? That is what this measures. That is why it is called susceptibility. Now, once you go, this is linear. This equation is linear. If you plot the magnitudes of P versus E, that is what is plotted here. Polarization. So if you do that, then what you have is a line. So how do you describe what is beyond that? So here we can't escape. We have to describe the nonlinear thing if you want to understand, do the photonics technology. So we add something to it. What do we add to it? How do we? This is to understand. This is only our artifact to understand, to explain, and then make devices. We need to do that. So what is happening in matter when this happens? We'll come to the equation later. So in the case of some answer has come good. Linear optical response, all the reflection, diffraction, everything is determined by the refractive index and susceptibility. Linear. This is called the linear. That is called the linear susceptibility. But the nonlinear optical properties are going to depend upon intensity, high stress. That is, high electric field, optical electric field. That's what happens. And you have a lot of interesting phenomena. The physics of it is, the large optical intensity causes a stronger perturbation of the Coulomb field. And you have new kind of transitions, etc. happening there. That leads to nonlinear interaction. And we can make use of it in optoelectronic applications. So this is basically the difference between linear and nonlinear optics. So how do we describe this? Even before that, I would like to tell you, I would like to show you something which all of you might have. Many of you might not have been exposed to nonlinear optics, but all of you know, might have heard the second harmonic generation. What is second harmonic generation? You have a light of infrared, and you may get light of red color, and you may get a blue color coming out of it. Frequency, a given frequency, and of course this also will come out of the sample, but you will also have the other This is there in the NDR laser. For example, 1.06 is infrared. So you can't even see that. That is rather easy to make, that laser. But what we want is green light. For many applications, green is the preferred color for us because of the eye sensitivity. So for that, you need to do this. You have to double the frequency and half the wavelength, and then you get 536 coming out of it. So this ruby laser, it will be red and blue, reddish and bluish. So this process is called second harmonic generation. But the second harmonic generation is actually a special case of a mixing of this kind. Green plus yellow giving infrared plus ultraviolet. Omega 1 plus omega 2 giving frequencies, sum and difference frequency. This will be high frequency and this will be a lower frequency compared to the original frequencies. So why am I saying that at this stage? So this is a well-known optical, nonlinear optical phenomenon. And here in this omega 1, put omega 1 is equal to omega 2, then you get the second harmonic. So it is a special case of the second order processes, second order. This, I will explain what this is immediately. And this, why am I highlighting this in the beginning is, this is the mechanism of getting a tunable laser today. If you want to buy a decent tunable laser today, the tie sapphire and all that. So that all that works on different orders. I have just shown one small part of it, that different orders of mixing happens there. And that, what does it generate? From 1 omega or 1 omega 1, omega 2, we get all that. Omega 1 plus omega 2, omega 1 minus omega 2. So using similar processes, you get a large number of frequencies and you can tune the frequency. Remember, laser has a specific frequency, specific wavelength. So tunable laser looks like a, what you call oxymoron or whatever. Tunable, can you turn it? Yeah, you should be able to get that monochromaticity at different wavelengths according to your requirement. That is tunability here. Let us look at the first experiment of nonlinear optics, which you have a laser here and you have a lens here, and this is a sample. Quartz crystal is a sample. So other things are not important. What is important here is the quartz crystal and the light. When light falls on, this is the red 693, and when that falls on it, it will generate, the red will pass through, but also there is a blue coming out of it, which 340 or whatever, 347. It comes at 347. And how did they detect it? This is the first experiment. How did they detect it? Oh, sorry, this is just a prism. So the role of this is just to separate the colors. Why do you need to separate the colors? Because a lot of red comes out, a little blue comes out. It is roughly less than 50%. So you need to filter it. Otherwise, you won't see it in the intensity of the original beam. So you need to separate it. And then how do you measure it? You put a photographic plate. So one spot, large spot will be there at the original frequency. And then there will be a weaker spot here. This is how you detect it. And this is how they detected it. How does it look like in a lab? This is a sketch. So how does it look like in an actual lab? This is from Cochin University. This is the sample here. This is the crystal here. And just like this is translated into reality. So the big boxes are just some filters. Liquid filter. Put some dye so that the other color is filtered off, what you don't want. So here you get a laser and 694 is the input. This is the sample. This is where it happens. And what you get is, of course, you get this, and also you get 347. That's what happens. And this 347 is the second harmonic of 694. So this is the well-known experiment which many of you would have heard of. Now, a very interesting thing. What you are looking at is a paper published in Physical Review Letters, probably the most prestigious physics journal. And what you see here, if I don't know whether you can read it very clearly, but I will read it. You see a scale. What is that scale? This is actually a photograph of the spectrum they took in this thing. This is the output where you have a spectroscope. So this is a photographic plate, and you will see two spots depending upon how you shift where you send the beams. So this is what they put as a proof. Remember, they are breaking it's a new discovery. They are announcing a very new discovery in science. So the paper must be written carefully. So they wrote it very carefully, and they wrote it like this. And at 690, you will see this big spot, high intense input beam. That is the input beam. That is from it is separated by the prism. And then they see, let's see, this is a direct reproduction of the first plate in which there was an indication of the second harmonic. Where is the indication? The wavelength scale is in the units of 100 angstroms. So the scale is 100 angstroms. The arrow at 3472 angstrom unit indicates a small but dense image produced by the second harmonic. The image of the primary beam is very large due to halation, various optical effects. So the point which I invite your attention here is this. The second harmonic, this is the original. There is no surprise about it. The surprise comes here at the arrow. If you look at carefully at the arrow, do you see a spot there? They say there is a spot, and that is the proof on which the paper was published. And the whole physics optics changed after that. Look very carefully. Can you see a spot? You can't see a spot because there was no spot there. What happened? Is a scientific fraud or something? No, no. The fact is, there was a spot actually. It is a very small spot. And the printer thought it is a mistake, some carbon particles, so he just removed it. The editor, reviewer, everyone accepted it. But finally, it went to the printer in the press. He thought, what is this dirty thing? Let me remove it. So he removed it. And it got published like this. You can go and refer to this paper. So that is the first experiment in nonlinear optics. Now let us come back to what exactly is nonlinear. So this, we said this is linear. And what is plotted here? The quantities of interest are polarization and susceptibility, and of course electric field. These are the quantities of our interest. How do you modify this? So this we have already mentioned. So how do we modify this? Let us go back and look at examples of some nonlinear systems. The pendulum, the simple pendulum, like there was a exam and an external examiner was watching a student doing the experiment. So the student is doing simple pendulum experiment. So he wanted to impress the examiner. Simple pendulum was going like that. That is no longer a linear pendulum. Your equation will not be valid. You know that now. There was another student who also wanted to show that he's very careful. So this pendulum was moving and he was very carefully, every 20 here, taking reading. And exactly after 20 seconds, he stopped the stopwatch. The pendulum was still going. He got out of the pendulum and stopwatch was still running. Okay. So this pendulum, you know, sine theta equal to theta, that is approximation we make. Approximately it is equal to theta. So that is applied to the spring system also. This is called the linearized pendulum. But actually, what is the truth? Is it G by L? You know what these things are, right? This is the basic equation for the oscillator systems. This is a pendulum. Actually, the real pendulum has a sine theta there. Instead of theta, you have a sine theta sitting there. So this will be true. Your equation will be true only if sine theta equal to theta, which happens very close to 0. So this is the problem. This is the difference between linear and nonlinear. You already know the concept. If you oscillate it with high amplitude, you are not going to get a linear pendulum. That actually becomes a nonlinear pendulum. So when I said nonlinear pendulum, that is not the meaning. Nonlinear pendulum is not like that. This only. It is the same thing. It is not this, but this is what it is. Similarly, nonlinear optical medium. Don't think that I twisted my specs so much that it becomes nonlinear, suitable for nonlinear optics. That's not possible. Mathematically, this is what is done. So you take the first approximation. Sine theta is approximate. So we are going to do something in this spirit. So as somebody mentioned, quadratic and other terms will be added to this. So there is something called Einstein's summation notation. Some of you, the students, may be knowing it. I will explain what it is in the next slide. But what it says is, you do a summation of this quantity, x to z, x, y, z. This stands for the summation is over x, y, z, the 3 Cartesian components. And the ith component of polarization is related to the various components of the electric field. That's what it is related. I will expand this equation and then you will get a clearer picture. At this stage, I have to mention, in some books you will see an equation, even in many places, you will see the second time written as something into E square, then something into E cube, which is actually wrong. Why is it wrong? Because E is a vector P is a vector and E is a vector. So the next term, E square, how do you understand the square of a vector? If you do E dot E, you get a scalar. So vector will be equal to a scalar for the second term. And the third one is E dot E dot E, which will be again, we don't know what it is. So that is going to be a complicated object. The reason is there are actually tensors. Physical quantities are actually represented by tensors. In all my teaching experience, I have one thing which I can never forget. If I go to a class and during my teaching, the moment I mention tensor, all the students get tensor and tensor. Actually, that is not required. Tensor is only to make your description perfect and quantitative. It's a method to use, physicists use very often to tell complicated things in a simple manner. That's what the tensor is. So this, instead of this is written. Or when you see an equation like this with a repeated index, it means it is actually, it refers to a summation where I and j are summed over x, y, z. In this equation, only the one component is looked at. So how does it look like really? This quantity which is written here, this is pi. So one component, px is written here. Now the important thing to note here is a nonlinear dependence. Px, the polarization along the x direction, is not only dependent on the electric field in the x direction. It depends on the electric field in the y direction and the z direction in general. The same thing happens when you hang a wire. When you hang a wire, what is the response and what the stimulus? You are applying force in this direction, in the vertical down direction, but where is the strain happening? Where is the length change happening? Obviously, it is getting elongated. So you will say, okay, length change is also happening. The cause is happening in the vertically down direction, and the effect is also along the vertical down direction. But do you notice that if a wire becomes longer, it also becomes thinner? So it is happening in the other direction. The force, I am pulling it this way, the effect is also happening in the perpendicular direction. So the whole picture is this. So each component Px, Py, Pz will be very intricately related to the various electric fields. And that is where the language of the matrix and language of the tensor becomes important. So you can write the various components for P1, P2, P3, and you see that chi ij has all these components, all these 9 components. This is just 1, 2. I have written xy instead of xy. I have written 1, 2. That's what it is. Now let's complete this part. Okay, we decided to add something to it. What do we add? So this equation should be written like this for a particular component, I component. So if you take it, you will have terms like this: chi ij ej, then chi ijk ej ek. The next rank. So the xn. This is not a superscript. This is actually, this is not a power. This 1, 2, 3 are the order of the susceptibility. So this is not just one susceptibility, but many. In this language, the first order nonlinearity is actually linearity. And it will be an n+1 rank tensor with 3 power n+1 components. That's what one example we have seen just now. Even linear. What the tensor, the susceptibility I was talking about here, is linear. It's a linear susceptibility. We are not even gone to nonlinearity. So when you go to nonlinearity, it becomes even more complicated. Higher dimension is added to it. And what scares students in nonlinear optics is this actually is a tensor quantity, and this is a complex quantity, and this is the frequency dependent quantity. All the 3 are important. They have their own significances. Complex quantity, absorption and dispersion, and then frequency dependent quantity, it depends on the frequency. So different colors, it will be different for different colors and all that. So this is what happens in the case of nonlinear optics. This is the nonlinearity which is coming in. Now, this is the usual. Please remember that this usual susceptibility which is related to the refractive index. The other terms are called related to the nonlinear refractive index. So here, which is more important? Why did I stop it with 3? Actually, I should not stop it with 3. I think there are reports on higher harmonic generation. If I remember correct, something like 55th harmonic and all that is standard nowadays. When I was a student, only this much was there. Chi1, Chi2, Chi3. But when my student, I guide my student, they were talking about high harmonic generation. High harmonic, 55th harmonic, not just 1 or 2. So mathematics has become very complicated. I'm glad that I will be retiring shortly. So this is what is happening in the real life. So the subject has become very complicated. And what do you get? Okay, second harmonic from the infrared, you get a green light. Third harmonic will give you violet, ultraviolet. What about 50th? It will be X-rays and things like that coming out of the laser. So people are using it actually for X-ray generation, gamma ray generation, and all that can be thought of. So that is the real glory of it. And why is it possible now? Not possible 25 years back or 30 years back. The reason is that now you have extremely powerful lasers, which also was mentioned earlier in this one of the talks. So this is the objective which we have in nonlinear. This is what this quantity chi, higher chi, chi2, chi3. This is what governs the nonlinear optical phenomenon. So there is energy transfer many ways. In nonlinear optics, we have energy transfer, wave mixing happens. How do the waves mix? How does the moonlight and your torchlight mix and even exchange color? How do you get different colors out of it? That is the fun of the whole thing. Before that, one more point. Which is the easier experiment? Linear optics is Chi1, okay, all Chi. And for this talk, let us, okay, at least for the beginning, most of this talk, let's ignore the higher powers. Let us forget all this Chi4, Chi5, all this thing. We will talk about only 3 of them. And then, this is not important. Actually, this has a very large magnitude. This has several orders of magnitude, smaller magnitude. And this has several orders less. Magnitude is several orders less. So, if you want to, let's ask the question, when will I see a nonlinear optical phenomenon? You will see a nonlinear optical phenomenon when this term, the term together is very large. If this term has to be very large, you have 2 possibilities. Either this has to be very large or this has to be very large. If this is very large, I mean, when I say that, I mean the property of the medium. So I should have a medium, material, which will have its second order susceptibility or third order susceptibility large. Or if I can't get that, take an ordinary medium and then you apply a very high intensity laser. So it is the product which you are interested in. If the product is large, comparable to, it will never be comparable to the first step. If it is large enough to see, then we will see nonlinear. So there is nothing like nonlinear media and linear media. You'll say air and water are linear media. No, they are actually, people have, Dr. Jaita has shown you an experiment in which water produces all the colors. So that is not really, that is no longer linear. But normally we say glass, water, air are linear in the sense that with reasonably low intensity, you can't observe this. This product is going to be very small. In fact, everything is nonlinear. Having said that, let me ask the question. So which nonlinearity will be the most important? This linearity we know. So you would think that, okay, this thing is very large. So this will be the most important nonlinearity. This is what we saw in the second harmonic generation and all that. But actually, it is not. It is this one which is most important. Why? In the sense, I will explain my statement. This is available only in very, very few crystals where the symmetry, inversion symmetry is not. That is the condition for this to be observed. So there is a symmetric constraint on it. It's like a dipole. If you have a positive sitting here and negative sitting here, you have a dipole. If you have positive sitting here and positive sitting here, you don't have a dipole. Okay? So, okay, quadrupole effects are there, but ignoring that, we will say that this is available only in very select media. Very few crystals. You know how many crystals have inversion symmetry and how many of them don't have and all that. So this is not. This is okay, but this is useful. So people go after those crystals, make it and use it. But so here, on the other hand, this 3, this everything, every material, everything is nonlinear if you have a sufficiently high intensity laser. So this is the most important thing. Another reason is that though the magnitude is small, it leads to many other interesting phenomena, offering control. That's what we started with. This can do at best only the second order can do only the change of color, change in frequency, mostly. But third order can do change of frequency addition, subtraction it can do, but it can do much more. And if time permits, I will show you some glimpses of what more it can do. So this is the perspective of the magnitudes and the effects, the various order effects which are important and all that. Okay, when you take up your research, maybe the 55th order is more important, but for, right now for the next 10 minutes, it will be the third order which will be more important for you. Okay, let's talk about wave mixing. You all know the Maxwell's equations, and you can easily show, if you come for interview for PhD in IIT, it will ask you to write these equations and derive that wave equation. So you do some tricks with your matrix vectors, and then you finally get your equation. This equation is very difficult, highly, just appreciate it. Let me spend a few minutes on this equation. This is a linear equation, this is a linear wave equation. This is so fantastic equation, philosophically too. Why do I call it philosophical? Because you have a derivative. Actually, it's a mathematically a tough one. It involves a differentiation. And it's a differential equation. Tough. It is a second order differential equation. Tougher. And it is on two different variables, on time and space. So it is indeed a very complicated equation. But, okay, now the philosophy comes here. This, here we have a del square sitting here, which is the space derivative, xyz, space derivative, derivative with respect to space. And this is derivative with respect to time. This cursor is sometimes, this is with respect to time. So you are mixing up space and time. And what happens when you mix space and time? You get motion, something moves. What moves? Look at this. What is mu0 and epsilon naught? If you multiply mu naught and epsilon naught, we told that in the first lecture, you get the speed of light. Invert it, take square root, you get the speed of light. So light comes out of it. You have a spatial derivative connected to the temporal derivative, double derivative, and then you have light coming out of it. So that is the equation. And in the case of the nonlinear optical equation, the linear equation will be modified by introducing the higher order polarization there. And that is the one which mixes up the wavelengths. And that is what we get. And that PI there is this. It involves. Where is the mixing happening? You can see it here. EJ and EK, EL are mixed. And what are EK and EJ? Different waves which are interacting. So that's what I call by the wave mixing phenomenon. In the earlier example, both were the same. Omega 1 and omega 2 also we discussed. So two different light waves. So energies get exchanged. Wave mixing happens. And that is the heart of nonlinear optics. For example, you can see that in this. The wave mixing, how it happens. Actually, it is very easy. These are all sine and cosine functions, right? E, for example. So you have multiplication of two of these things. So multiply. What is cos A cos B? You remember what is cos A cos B? You will see. Okay, there is another homework. What is cos A cos B? You'll find out that. And sin A sin B, all those things. So you know where this mixing comes out. That's wave mixing. So wave mixing occurs through nonlinear polarization. So that is the story. That is what makes light control light. That's the importance of. So that with that I sort of come to the detailed part, and then I will talk about different processes. I talked about different processes. I already mentioned. What I wanted to mention here is that second order has limited possibilities from the application point of view, but third order nonlinearity has many more possibilities. You can access forbidden transitions, what is called phase conjugation, error correction of the images, and then self-focusing, switching, all that. We may just touch upon some of this in the next 10 minutes. I started 10 minutes late, right?
Yeah, yes, sir. You can take no issue.
The medium behaves like a lens, and a parallel beam gets focused. This is the process of self-focusing. How does it happen? It happens because the refractive index becomes, now refractive index has two terms. N0, which is the usual 1.5 for glass and 1.33 for water, the linear, what you are familiar with, the normal one. And then there is an intensity dependent term, N2I. N2I is the nonlinear refractive index. Not only N2, N2I is the refractive index dimension also. So you have an intensity dependent How do we know that? How do we understand this? Switch off the high intensity or make it very small. High intensity. If you switch off the light, then there is nothing. So if you make it very small, I is very small, you can neglect this part and you have your 1.33 back or 1.5. Okay, so that's a linear. That's what's called the linear. And this is a very small quantity, 10 power minus 8, depending upon whether you are working in CGS or SI and all that. But whatever it is, it's a very small quantity, and that small quantity can make a lot of difference. Now let us understand how does it focus. What is self-focusing? Without a lens. Without a lens, light can focus. How does it happen? I said it is related to the N2. And actually, there is a little confusion here in the sense N2 refers to the third order. Why? The first fellow called it like that and published the paper. So everyone, we all call it N2. It is not related to chi2. It is related to chi3. It's just some factors multiplied by chi3. That's what it is. So we can say it is chi3. So chi3, how does chi3 make the light focus? That is called self. That's the point of self-focusing. So let us look at the concept of a wavefront. What is a wavefront? You know that wavefront is the locus of points at the same phase. Okay, that is why from a point source you have spherical, from a tube light you have the cylindrical waves and all that coming. Now let us see. There is a family of doctors. The grandfather is a big famous doctor. The grandmother is also a doctor. The parent, uncle is a parent. Everybody are doctors. Even the children want to become doctor when they grow up. So there are children, the young child onwards to the grandfather. And there are doctors, so they are very health conscious. So what do they do in the early morning? They all go for a run. Imagine, you have to picture this. I should have put a picture there. You should imagine a grandfather, fathers, uncles, parents, everyone, and then the children going. And they usually go in such a way that the grandfather goes at the middle. And this side, the father, mother, uncle, aunt, like that. So the oldest person runs in and the children run on the last. So they hold a wire, they hold a string. This is the string theory of nonlinear optics. All these people hold a string. Okay, is your picture very clear? Grandfather, father, mother, uncle, aunt, everyone. And finally children at the end. And they all hold a string and they all run. Now you will be able to tell me what happens to the string. What happens? Initially it will be parallel. The string will be straight. The string will be straight. Because they're all running. Initially almost at the same speed. But very soon the grandfather gets tired. And the parents get tired. But the children are still running. Then what happens to the wavefront? I have already explained what I am going to explain. So that is what is happening. Now forget the grandfather and the children. We will talk about light. Laser. Let us look at a laser light. Oh, I said let us look at a laser light. If you want to look at a laser light, you can do it only twice in your life. First with your left eye and then with your right eye. So don't look into the laser light. But look at the cross-section of in a CCD or something like that. What you will see in most of the lasers, high intensity at the center and low intensity at the periphery. That's what you will see. So middle, high intensity, at the end of the beam, the periphery of the beam is low intensity. And that is what is happening here. So this is the grandfather at the middle and children at the end, they're all running. And then when it enters a nonlinear, when I say nonlinear medium, high chi3. When it enters a chi3 medium, this factor comes in. So the refractive index is C by V. So the speed is getting affected by the intensity. So the speed of the middle part of the wavefront is small compared to the speed of the other part. So the beam gets curved. That is how it curves. This is how it's quantitatively understood. There are a lot of phenomena related to it. And this is actually very interesting. The story doesn't end here. The story doesn't end here. What it does afterwards is even more interesting. You have spatial soliton, temporal solitons, and all that, and many other wave mixing phenomena happening from beyond that after a critical power. But that is another interesting story. Later I will tell you where to read it. So all these are technically understood. Why is it important? Here there is what is called filamentation. A beam, narrow beam gets focused into different filaments, and many other things happen which I may mention later. And there is shape maintaining beam, all those possibilities are there. So these such beams can go for a large distance. These are the possibilities arising out of this phenomenon. And by measuring the beam profile, changes in the beam profile, you can measure the nonlinear refractive index indirectly, because this is because of the chi3 and n2. So looking at it, you can measure it. And the other aspect of nonlinear thing is you can make nonlinear absorption possible. What is meant by nonlinear absorption? You know what is optical absorption? You have a level E1 and you have an energy level E2. So if you give exactly E2 minus E1, that quantum of energy, then only there is a transition. മുമ്പൊക്കെ കേരളത്തിൽ വന്നു കഴിഞ്ഞാൽ പണ്ടൊക്കെ ചായക്ക് വിലയുണ്ടാവും, ₹1 ചായക്ക് അന്നത്തെ വില. പക്ഷേ ചായക്കടയിൽ ചിലപ്പോൾ നമുക്ക് ₹1 നമ്മുടെ കയ്യിൽ അപ്പം ഇല്ലെങ്കിൽ ഒരു ഹാഫ് ചായ തരാൻ പറ്റും. ഹാഫ് ചായക്ക് കൊടുത്തു കഴിഞ്ഞാൽ 50 പൈസ കൊടുത്താൽ ഹാഫ് ചായ കിട്ടും. So something like that is happening here. So here you have, if you have enough E2 minus E1, then that quantum will pass through. But what happens when you don't have E2 minus E1? So what physicists do when they face problems is they sing classical music. So people sing classical music. And then what happens? You can have transitions like that, 2 photons. So this is actually a form of nonlinear. This is this should be simultaneous. It is not exactly like the picture which I have shown. It's a simultaneous absorption of more than 1 photon. And then this is called the nonlinear absorption. So just like linear absorption, you have nonlinear absorption, and you can access energy levels which are not accessible by it. You can have many more. And how do you measure this? This is very interesting. I have a better picture. I will explain how it is measured. So the point here is that you can have multi-photon absorption with more than 1 photon participating in that. And you can access different energy levels and many other things. Even multi-photon microscopes are now available now. The nonlinear microscopes are available now, which offer a lot of advantages, which I will not get into, but I will tell you where to read about it. So this is called the Z-scan experiment. So let me ask a question to students. Can you use a convex lens as a diverging lens? No, everybody thinks convex lens means converging. That's all you think. But in this experiment, we use a convex lens as a diverging lens. Don't limit your thought to the focus. Yeah, if you go up to the focus, it is a converging lens. But suppose you are standing there, then it is a diverging lens. What does this lens do to this laser? If you are standing here, it diverges literally. Okay, now the point is, it modulates. This arrangement modulates the intensity of laser along space, along Z. Okay, how do you understand that? I have extremely high intensity here and comparatively low intensity here and low intensity here. Suppose I am moving a detector like this. Then high intensity here and low intensity here. So I am modulating space. Right. And then suppose you move an ordinary material like a glass plate or water along this. And then plot the intensity as a function of distance. Nothing happens, nothing happens, then you will just get the same intensity everywhere. Imagine you take a glass piece here and move the glass piece and measure whatever is coming out here as a function of the position. Then you will get a straight line. But in the case of a nonlinear material, if you move a nonlinear material through this, then here something happens. Here nonlinear absorption happens. And because of nonlinear absorption, you will see a dip at the focus in the output intensity, which is measured as a function of distance. So from this, you can easily measure the susceptibility of the refractive index of the medium and the susceptibility of the medium. So you get something like this typically. If you measure all the light coming out of here, then you can see that there is a difference. Why is there a dip? Why there is a dip? It is because there is nonlinear absorption happening here. And that happens when the sample is here. When the sample is here, it doesn't happen. When the sample is there, it doesn't happen. So you get the usual thing. But when the sample goes and sits here, high intensity. And then, of course, nearby, little less intensity like that. So you get a typical. So this is an experiment to measure. The experimental setup may look a little bit complicated. Let us skip it. Some other details I am not getting into. One of the applications of that is you can use it for optically smart materials. to design optically smart materials. What are these materials? You send it through this sample and measure the optical output. And then if you plot the output intensity as a function of input intensity, you will see that it saturates at some value. So this can be used to protect your eyes or your detectors and things like that. This optically smart materials is one area of application. This is an ideal diagram, and this is something you will see in the experiment. And one topic which I want to go quickly is the Nobel Prize topic. But don't think that I'm going to explain it thoroughly here. I'm not going to do it. My learning objective here is that at the end of the talk, you will go and read the Nobel lecture of Donna Strickland. Okay? Is it clear? My learning objective is not that you will be thorough with this, but it is just that after the next few slides, you will feel like going and reading the Nobel lecture of Donna Strickland. Chirp. The idea of chirp is very interesting. The frequency of the wave is not the same in time. What is frequency? 1 by time. And 1 by time is not the same at every time. That's what happens. Chirp. The bird's typical chirp. This is called chirping of the birds. And this is very important. And it is actually a complicated matter, not very easy to explain in the remaining time. But as I said, my motive is that you should go and read how nicely Donna has written it, so that in a Nobel audience, everyone comes there. So she has explained it in a very nice manner. There is a lot of, you can describe this. There will be a modulation compared to the plane wave solution. You will have modulation where the various parameters can be put in. And the important factor here is the nonlinear phase. Because of the chi3, a nonlinear phase will be introduced. And that nonlinear phase is related to the N2. The refractive index, the chi3, that's the chi3 sitting here. So in fibers, it is very easy to get this kind of things. So you can have different slopes for this N2. And if N2 can be positive and negative, it can work as a convex lens or a concave lens. Depending upon that, you have different features in the dispersion curves. And that ultimately leads like this. So the different components of the wave packet move with different speeds. So there is different time delays are introduced, so the pulse disperses. So this is the technique which Donna and others used. Some of you are aware of this group velocity and group velocity dispersion. Group velocity and group velocity dispersion, normally I take at least half a class to explain that in my regular course. So I'm not attempting that. And then you get the Nobel Prize. So this is what happens. So what exactly did she do? Again, you can read it, but I will quickly go through. You take a pair of gratings and send it through that and disperse it. And then you have a low intensity thing, and then you send it to the amplifier and amplify it later. And this will, if you play with the space and time domain, this is called CPA, chip pulse amplification. And then you get a very high intensity. What is written here is that the CPA technique revolutionized laser technology. It enabled the emission of very intense short pulses of light using an intricate method to avoid the risk of destroying the amplifying material. Instead of amplifying light pulse directly, it is first stretched in time, reducing its peak power, and then it is amplified. And you get huge enhancement. And the time, it becomes a femtosecond kind of pulse. So this is basically, in one sentence, this is what they have used. And this is a slide from the Nobel lecture, which it's available free. You can just search for Donna Nobel lecture, and you don't have to remember any HTTPS and all. And this, it leads to all the other interesting phenomena. Once you get a femtosecond pulse, I think many things were mentioned about femtosecond pulses and their application and all that. One thing, of course, you can see at different time scales. See, if you watch a serial, nothing much happens. If you Monday, Tuesday, Wednesday serial, not much really happens. So you can skip it 2 weeks, don't see the serial and come back and okay, still you get the story. But the subtle jokes and all that you won't get. For that, you have to watch every incident of the serial. Similarly, in a complicated chemical reaction, if you want to know what happens in detail, in temporal detail, then you have to look at that particular time scale. Catalyst, for example. Catalyst A plus B, I think I mentioned this earlier also. A plus B plus C catalyst gives you AB plus C catalyst. So what happened to C catalyst? Nothing happens. That's what you will think if you look at the usual time scale. But if you probe at the femtosecond atomic and molecular motion happens at that time scale, then you get more information about the detail of that, what is happening at that. Okay, another interesting thing is the thing which can happen is the white light generation or super continuous generation by a process which is complicated, which I am not going to describe now, but I will tell you where to read about it. And that will a complicated process of nonlinear optics gives you finally the superconducting. So you have different colors coming out of. So this is something like the opposite of Newton's experiment. Use white light and make different colors. Here we use some color laser and mix all the colors using extreme nonlinear optic and finally produce white light. So this is the process which happens there. And why is it important? See, this again from Donna's lecture, and you can see various processes here. The stopwatch which measures a second. I mean, I'm not intending that you will be able to read it, but I mean, it's too small. But when you project a PPT, don't project like this, but otherwise you read it out. The fast camera shutter works in the millisecond time scale, chemical reactions at 10⁻⁴. And microsecond, and then fast electronics at nanosecond, and all that. Molecular vibrations, photosynthesis, electronic motion, and that happens at attosecond. I think Jayita mentioned some of this. So that is the significance of the Nobel Prize. All this is possible because femtosecond light could be generated. There are two things. The pulse becomes thinner and it becomes taller also. So at the typically students are of the age 20 or all that, and your parents will be telling, why have you become thin? Now you have the answer. I have also grown, so I have also become taller. So don't worry about it. You can tell your mother. Okay. So this is the importance of the Nobel work is that work makes use of nonlinear processes to make a femtosecond pulse with extreme intensity availability. Light is manipulated in such a way that it's the width, the pulse width is reduced and the intensity is very large. So where do we go now? What is new in nonlinear optics? Many things are happening in nonlinear optics. Wave mixing for tunable laser action, that's what we have seen. And you get tunable laser including ultraviolet, infrared and all that. And generation of higher harmonics. I'm not talking about Chi3, I'm talking about Chi55. So you generate all kinds of things in the electromagnet. This is what you are going to see in future. And then extraordinary matter. You remember what I said in the beginning. Extreme light interacting with extraordinary matter. That's what is happening in nonlinear optics. Extreme light, extreme kind of light is now behaving with extraordinary light is behaving. Femtosecond laser is much extraordinary compared to even ordinary laser. And that is interacting with extraordinary matter. 2D materials. Slow light structures, BEC, all kinds of new kind of things. And you have local field enhancement and many other phenomena which is happening. And then the ultra-fast nonlinearity. So that is the perspective. This is not even complete. Even while I am talking, new discoveries are being made in various aspects of this. And today, if you are going to take up research in optics and you are going to do light-matter interaction, you will stumble around some of these things. In your research, you will see. That is why it is important to understand it now. Thank you. I thank the organizers, Poti and others, and Arunan, Dr. Arunan, Dr. Poti. I thank the funding agencies which have given us a lot of equipment to do these experiments, collaborators, students, and my audience. Again, in the second lecture also, I actually did not get a chance to talk about my own research work. You might have noticed. So what I'm going to do is, I promise you that I will give you the answer to all the questions which I raised. Where do you understand? You only mentioned it. So we normally teach here a course with 40 lectures on nonlinear optics. And what I have done for you is condense the 40 lectures into 1 hour, which becomes condensed matter lecture. That's what I have given you. So I am responsible for giving you a source where to read all this, how to understand all this. There are many books, of course, there are many books. But most of the books are at research level, and a student at BSc level will not be able to understand, will find it a bit difficult to start with. So for such students, Professor VIJAYAN, and who was also the research guide of Professor Vijaya and myself, he and I together has written a book on nonlinear optics, understandable for BSc students. It took 4 or 5 years to write this book. So, you know, 1 hour lecture can do only that much. And finally, as I said, I didn't have a chance to tell you about my own research work. So I will just give a reference. One of the recent, not the most recent, but you can read that to know a little bit about my interest in 2017. With that, I will close. Thank you.